Hello, everybody. Oops, I have to push. Hello, everybody, and welcome to this week's Hangout. It is time for our news from Hubble and across the universe with Dr. Frank Summers Hangout. We do this every month. Generally, we try to anyway, and it's usually coincides with our Hubble public lecture series, which is generally held on the first Tuesday of every month. We got it because of some scheduling issues. We're having it a little bit later in January. Plus, we had the AAS earlier this month. So we are having it in the last week of January, but that gives us a good opportunity to talk about next week's Hubble public lecture, which will be on Tuesday. It's generally rebroadcast on YouTube, so I'm usually on hand to respond to questions and comments while the lecture is going on, but we invite you to watch it after the fact as well.
So let me just give the plug promo for that.
Okay, go ahead.
Dr. Jason Tumlinson of the Space Telescope Science Institute. He will be speaking on one of the longest titles I've ever been given, From Cosmic Birth to Living Earth, the next great space telescope beyond JWST. So, I mean, we're already looking forward to the James Webb Space Telescope, which doesn't launch until 2018, but Jason's going to come and talk to us what happens after that.
Right, and we've also had a couple of hangouts on that as well. So yeah, so you're right. We are actually starting to look beyond the Webb Space Telescope. So definitely check that out. I will have it on. It's at 8 p.m. Eastern Standard Time, and that's when it'll be broadcast on YouTube. And so we'll look to see you there. Before we get started with Frank today, though, let me just tell you we hope you'll bring us some questions and comments for today's hangout. We have. I'm looking at the Q&A app. That's the best way to interact with us. But I'm also looking at Hubble Hangout hashtag, as well as the event page on Google+, and the YouTube page this is being broadcast on. So please bring us your questions and comments, and we'll try to read them out while we're on the air. Hiya, Frank. Welcome back.
Hiya, Tony. How you doing? It's been a long time since we chatted because we had AAS this month, which postponed this month. But
that's right.
Also last month, I was at the American Geophysical Union conference, and you had a vacation, so I don't think we did a December hangout.
No, we didn't do a December hangout, so we missed that one.
It's been since November, so welcome to all our friends who are joining us. There's a whole ton of stuff to catch up on. We're not going to get through it all today, okay? Unfortunately, because I got so much cool stuff just from one image, really. Well, one press release. It's just really lots of fun.
Okay, so yeah, so go ahead. What do you got for us?
Okay, so I am going to talk to you today. This is our news from the Hubble and across the universe, and I will speak my story for today. And I apologize there isn't more than one story today, but we got lots of cool stuff here about this. Okay, revisiting a legend. Okay, we have certain legendary images. When you think of Hubble, there are certain images that you say, wow, that's something that just is so cool, that will live forever in your memory of Hubble. I think perhaps the most famous image Hubble has ever released is this one, the pillars in the Eagle Nebula, poetically named the Pillars of Creation.
When did that first come out?
This one was first released in November 1995.
Yeah,
okay?
That is definitely an iconic picture.
Yeah. And matter of fact, you know, in November 1995 was an amazing month for us because not only did we release this image, but we also released that beautiful image of the trapezium cluster in the Orion Nebula. That first Bob Odell image of the Orion Nebula getting into the trapezium, it was like 5,000 pixels across by 5,000. It was amazing. So that all came out within 1 month. So that was a good month for us. But this one is one that people always remember, and it's nicknamed the Pillars of Creation simply because these are places where stars are forming. All right, so you have these long, tall pillars, and they're being blown back by gas from hot stars that are forming in this cluster. And in the very tops of these pillars, and I'll show you some of the details in a bit, are places where stars are actually forming. And so hence that's where the nickname Pillars of Creation comes from. But let's back up a little bit. Let's actually give you a little more context for this. We're going to explore this in great detail. So this is an image of the Milky Way, center of the Milky Way galaxy from Akira Fujii. Kira is wonderful and lets us use a lot of his images here at Hubble. And what has been drawn out here is the locations of lots of different Messier objects near the galactic center. You can see M16, M18, M25, M23, M20, etc. But the one that's been boxed in there is M16, and that is the Eagle Nebula. Now, some of you may not know when you're looking towards the galactic center, you're not going to have this good seeing. Just to show some of you, the constellation Sagittarius is drawn in the lower right, and I'm going to put in the constellation lines for you. The constellation lines, yes, the teapot. This isn't the entire constellation of Sagittarius, but it's the only part of the constellation of Sagittarius that I know. Okay, so
yeah, it's a part everybody recognizes. That's what I all learned on as well, is how to find the teapot.
Exactly. You got to find the teapot, and then you're actually looking towards the center of the Milky Way. For those of us in the northern hemisphere, you're only going to be able to see this in the summertime, July and August, and it's going to be low on the horizon. All right, so the center of the galaxy is not going to be visible in winter. It's only visible in summertime, and it only gets, you know, tens of degrees, 30 degrees or so, 40 degrees above the horizon in the summertime, and that's when you can see the teapot. Okay, and for those of you who think of astrology and think of that you're born under the sign of Sagittarius and that you're supposed to be a goat herder, no. Remember the song we had? You are a little teapot. Okay.
Don't sing it, Frank.
I won't. You didn't like my singing last time.
Oh, it was fine. I'm just not going to join in. That's all.
Okay. Anyway, so there's your teapot. All right. So let's zoom into M16. Whoops, I hit the wrong button. There's the button. Okay. So this is a beautiful image. It's a ground-based image from a website called clearstarrynights.com. I couldn't find the name of the person who does these images. He didn't put a lot of these websites put their names and their credits all over the place, but this shows you perhaps why it's called the Eagle Nebula. I wanted a wider base view so you can see sort of the wing extending to the lower left and the head up at the top left, and the spread of the wings of the eagle sitting in front of you, right? You can sort of, can you see that, Tony?
Yeah. Do you have the ability to use your cursor at all to kind of circle what you're talking about, or?
I do, but it's that this screen is such high resolution.
Oh, yeah, I can see it though. Go ahead and circle.
Okay, all right.
Circle where you're talking.
Here. There you go. Okay, so that's the head.
Yeah.
Okay, and then if you follow down here, you can see the wing. All right.
Okay.
And then back up to the other wing. The other wing is not so sharp. Maybe he's got the other wing folded in, right? Okay.
So that's how
I see the eagle.
This is is it a red wavelength image? Do you know what filters
well, most of the nebulae in the universe glow in the light of hydrogen alpha, right? Because most of the gas in the universe is hydrogen, and the excitation line of hydrogen that gets excited is hydrogen alpha, which is a red wavelength.
Right, 65, 62 angstroms, I believe.
There you go. So the point is that most nebula appear red, which is one of the reasons why I went out to search for this image. One, to show you the eagle, but two, to show you what it really looks like. It isn't the green of the Hubble image, right? The green of the Hubble image is actually the oxygen line, colored green, so that it's not. The Hubble image uses very specific filters and doesn't show you what the human eye would see. This is a closer approximation to what the human eye might see. Okay.
Okay.
So where are those Hubble images? Well, you look in the center at the heart of the eagle, and you can see the pillars, and they're kind of fuzzy here. I'm going to switch to. Oops. Where am I? I'm hitting the wrong. I got two laptops, a laptop and a desktop in front of me. I keep hitting the wrong keyboard. So here, this is a zoomed in toward the center, and you can see outlined in yellow the three pillars from the 1995 Hubble image, taken with PIC 2, so it has that interesting chevron shape to it. Okay.
Wide Field Planetary Camera 2.
There you go, with PIC 2.
Yep.
Well, in 2005, we had a new camera on Hubble, the Advanced Camera for Surveys. And we took a two-pointing image of another pillar, what we called the spire in the Eagle Nebula. And you can see that also outlined here. So for Hubble's 15th anniversary, we did this image of the spire in the Eagle Nebula. And you can see it's very inspiring. It's nice here, but to give it more resolution on this small screen, I'm going to turn it sideways so you can actually see a little bit more, our viewers can see a little bit more of the detail.
Okay.
And what I like about this is that you see all of the material up here that's flowing off of the pillar. You've got the bright head to the pillar, okay, where the ionizing radiation is smashing into this dark gas. The high energy radiation is taking that dark molecular gas, heating it, ionizing it, turning it into ionized gas that's flowing off the top. You've also got this jet coming up the top here, okay, which is probably from. Actually, I don't think that's no, I take that back. That's not a jet. I'm sorry. I'm used to seeing jets. It's a little small in there.
Okay, you're pointing off to the right of the image right now, just in case people are having trouble with the cursor.
On the right of this image. So you've got this really bright region up here, and you've got this really long tail of material hanging in behind it. And it's a very beautiful and poetic image. And that's what we released for our 15th anniversary. Okay? So, if we go back to our 1995 image and we put it up here, we revisited this using our brand new camera, Wide Field Camera 3. Right? So the first image I showed you was with PIC 2, the one image I'm showing you now. The second one was ACS. And so we've gone back to the Eagle Nebula Wide Field Camera 3, and we've done a mosaic 4 pointings across it. And so at the exact same scale as the 1995 image, here is our 2015 image of the pillars in the Eagle Nebula.
I never get tired of seeing that. That's really nice. That's amazing.
You know, you and I have been staring at this all month.
Oh, I know. Yeah.
And it still doesn't lose its beauty to it. It's just amazing just how much there is here.
So go back to the 2005 and then just kind of go back. Are you gonna?
Actually, how about if I go to the next image?
There you go. That's why
I do an overlay. Okay.
I should have known you had it.
So to prep for this this presentation, I actually went through and got the highest resolution images, and I overlaid them and worked them because I'm going to show you all sorts of details about this, and show them how they look in one image and how they look in the other image.
So the green in the WIF-PIC 2 image you said was due to oxygen?
Right.
Okay.
So the reason why these aren't red is they aren't red, green, blue filters. Instead, they're very specific.
Hello?
Line. Okay. So that there are 3 specific filters designed to get the emission from 3 specific elements. And different elements will be excited at different temperatures. So in a way, each of the filters probes a different temperature structure within the nebula. And so the colors chosen in 1995 put the oxygen in green. The colors chosen in 2015 put the oxygen in blue. So that's why the color palette chosen here was different. Okay.
Just to keep things clear, huh?
You know, artistic. I mean, we were very inexperienced at creating these gorgeous Hubble images back in 1995. We got another, another 20 years of experience in doing this, and the artistic choice for the colors this time came out like this.
Okay.
All right. So let's compare. First thing that you see is that the WIF-C3 image, the 2015 image, covers a lot more area. It shows you a lot larger field of view, more pixels. Whereas the original image was 2.6 million pixels, our new image is 60 million pixels. So we've got 30 times the number of pixels to look at. But the resolution is actually about a factor of 2 better across the entire image. But there's so much more in the image. And let's explore a little bit of that. Okay?
Okay.
So, if we zoom into the center of the leftmost pillar, on the left you see the WIF-PIC, the 1995 image, and on the right you see the 2015 image. And there are twice as the resolution is a factor of 2 in each direction, So correspondingly, there's a factor of 4 times more pixels per unit area in what you're seeing. So you can see that for example, if you take a look at the ridge along here, okay, see that ridge along here, this ionization structure
on the right image you're pointing. Yes.
Yeah, I'm pointing on the right image.
Yeah.
If you look at the same ridge on the left image, you can see how it's just fuzzed out.
Yeah.
Right. You can see a lot more structure. If you look at this, I don't know, smokestack, this long dark black tube, and the top of that, and the detail that you can see there, you can see just a bit more detail in the 2015 image. And then at the very highest peak, at that point, that tiny little nib on there, you can start to see the structure.
Is that a scientific term?
Yes, these are technical terms. Don't try this at home.
Okay, so at the nib.
At the nib, you can start to see the structure. And so this is to show you that we aren't getting 10 times better resolution, but we are getting a factor of 2 resolution. And one of the science results that they came up with was that in 1995, they tried to measure the thickness of that yellow edge to the dark gas. It's called the ionization front. The thickness of the ionization front they determined was below Hubble's resolution.
Okay.
Well, they did it again in 2015, and you look at that, and you know what? It's still below Hubble's resolution.
Wow.
The crossover from this hot ionized gas to this thick, dense molecular gas is really, really thin. I mean, it's hundreds of parsecs. It's less than hundreds of parsecs at the distance of the Eagle Nebula. It's showing you that the transition region is really, really sharp. Something that we had, I guess, you sort of learn that in graduate school, that it's supposed to be a very thick, very, very sharp transition. But to see it in this amazing detail, it's really kind of cool.
So while you're on this topic, let me get Nicholas's question in here. Nicholas Grader from the Q&A app. The red line on the old image. Is that a cosmic ray hitting?
No, the red line on the old image is actually a diffraction spike from a star that's off screen above. If you look in the new image, you can see a diagonal line in the upper left.
Oh, yep.
That's the diffraction spike from the same bright star. Okay. So
it looks so regular though in the older image. It's just like a straight line. That's weird.
Yeah.
Okay. Yeah. So that's what that is, Nicholas.
Okay.
Go ahead.
So now we're going to move to the top of the middle pillar. Okay. And this is where in the Wide Field Planetary Camera 2, we had the PC chip, the planetary camera chip. The reason WIFPIC 2 had that chevron shape is you've got 3 chips that are the same, and then you've got 1 chip that's twice the resolution. So this would be the chip. This would be the spot in the Eagle Nebula where you'd have higher resolution in the 1995 image. Just this one small region in the 1995 image has high resolution. And so I wanted to show you this to show you that the resolution from the 1995 image is roughly comparable to the resolution in the 2015 image in this one region. Now, it's still not as good.
It's noisier in the older camera. It looks noisier anyway.
It's definitely noisier. The improvement in the detectors is apparent, but the improvement in resolution is not quite as apparent in this region as it was in the other regions. Just one little thing that I like to point out is I'm looking at the right-hand image.
Yeah.
You see that little thing there?
It looks like a jellyfish.
That's a jellyfish. Yeah. I think all these small little details start to pop out when you look at this new image of just all these small things.
Well, it's more than that too. I mean, you could see all the structure in the clouds too. I mean, like there's that big central feature there. It's just all of it looks so much more defined in the newer image.
All right. So let's go to the real highlight portion of the thing, the top of the leftmost pillar. Okay.
Yep.
This is where you can see from the 1995 image to the 2015 image, we get a significant resolution, all sorts of cool things going on in here. The structure in detail, and as you said, the structure of the gas is really apparent here. Just when the ionizing radiation hits this cold, dense gas, that gas ionizes and then it sort of evaporates.
You should talk about what ionizing is. I don't think people find
okay,
that.
Ionizing.
Yeah.
Okay, yeah, we do tend to throw that around with abandon. So ionization is when a high-energy photon hits an atom and liberates an electron. Okay, it puts energy into the atom, and the electron goes free from the nucleus. And so, one or more electrons can be liberated, and then your molecules or your atoms become ionized gas. Okay, and when you think of, we can sort of think of the ionized gas being set free from this dense molecular state, a little bit like the steam you see coming off water, right?
Right.
Going from this dense state to this gaseous state. And you think of it as flows, and you really can see, you can feel the flows of that material, the ionized gas, coming off of this dense stuff. Now, if you look down in the bottom, okay, you can see this jet down here. All right, and I'm going to zoom in on the jet at the bottom and show it to you. 1995 on the left, again 2015 on the right, and here's where you can truly see the resolution difference, right?
Right.
Now, this one is a jet. This is a jet from a newborn star. Inside this nodule here, just above center, a new star has formed. All right, and so a brand new star is formed. And when stars form, you've got all this material swirling around and crashing onto this new forming star. Some of the material actually gets thrown off into these bipolar jets, material streaming off in opposite directions. And so you can see the jet extending up and the jet extending down, spewing away from this newborn star.
So there's a star hidden in there, and in fact, there's star birth going on throughout this whole region, as you've already pointed out. But are there any? If you look at this more diffuse clouds in there, I don't know if you want to go back to that one right before that you were just showing, but there's lots of structure in the wispy area of the clouds. Yeah, this one. So on the right here, you can see all these sort of wispy cloud structures that look like almost like a magnetic field in the corona or something of the sun. Is that structure being? Are there any magnetic fields in there, or is it all just being sculpted by stars being born and the winds from all these the star creation?
Well, I would say that there are magnetic fields. First of all,
okay.
Their magnetic fields are but the magnetic fields are very small and very dense. So when you collapse material down to create a star, generally you're going to bring the magnetic fields along with it. You're going to concentrate the magnetic fields around the formation of the star. As a matter of fact, one of the things we believe that creates these jets is the magnetic field flinging material off in these opposite bipolar.
The magnetic field of that particular star, though.
Of that particular collapsed star.
Okay.
On
but
the
there's
scale
not is there a nebula-wide magnetic field, or is it just a sum of all the individual?
The nebula-wide magnetic field would generally be very low.
Okay. Okay.
So I would, I'm not an expert in nebula, but it would be my opinion that the magnetic field would not be strong enough to create the structure that you see in this gas here.
Okay. All right. Cool.
Okay.
Thanks.
All right. No, good question, because I actually have another point about magnetic fields in just a minute.
Okay. All right.
We'll play off of that. Okay. So you can see the resolution difference here. You can see this jet, but this jet is moving, right? The star is emitting this jet constantly, and if you go back to look at it, you can actually see the end of the jet moving between the 1995 image and the 2000. Well, it was taken in 2014, released in 2015. So on the left is the 2014 image, is showing you the region that we're looking at, and in the center is the 1995 image with the arrows. And then on the right is the 2014 image with the same arrows in the exact same place in the image.
So over 20 years, it's moved a few pixels. Do you have an idea what the distance is on that, or are you gonna? tell us that later.
I don't remember. I should have that. I remember. When we were at AAS, I knew that. Here we are, 2 or 3 weeks.
Forgot that fact.
Okay.
Okay.
Like, yeah.
But it can be figured out. One of the ways you can figure it out is we know what's something called the pixel scale of the camera. Right. In other words, how much area each pixel on the camera covers, and you just count the number of pixels, and that'll tell you
the number of pixels. And you need to know the distance to the Eagle Nebula, which is something like 77,500 light years, if I remember.
Mm-hmm.
So
okay.
It can't be very long. The entire pillar. The long pillar from the old image was about 3 light years in length. So this is very small fraction of a light year on this, right? So this is not this is solar system scale stuff. Okay, hundreds of AUs of astronomical units at best. Okay.
Okay.
All right.
It's good. I just want to give people a sense of how far this is moving, and when you know how far, and you have the time period, you can get the speed that it's going to.
Exactly. Okay. So that's the kind of cool stuff that changes from the 1995 to the 2014 or 2015, however you want to call it, image. But there are a lot of cool things that are new. Right, so let's go back to this whole overview image of M6 of the new image. And one of the things that you see, of course, that you couldn't see before is all this material down bottom. Right? And what I really like about it is that you see the material streaming off of it. When we looked at the old image, right, it sort of had this sharp bottom to it, right? And you couldn't really, and we talked about the ionizing radiation, the winds coming down past these pillars and pulling the material back and streaming the material back. Now you get to see that material streaming down off of it, and you can really tell that it is being pulled away by these winds and radiation. And of course you have this other structure down below, which I don't know, sort of looks like a stump to me. So I refer to that as the stump. But do you know Robert Hurt at JPL?
I don't know him personally, no.
Okay. He looked at this image and he said, well, hey, you know what? Let's single out just the center pillar. Right? And you can see the pillar coming down, and you can see the material streaming off of it. And you know what he said?
Right.
That's a Dementor from the Harry Potter movies.
I guess so. Yeah, I guess it does kind of look like that.
And ever since he and I chatted about this, I was like, okay, right.
Now that's all I can see. Yeah.
when you isolate it like this and you see the material, that's the visual effect that they did for the Harry Potter movies of the Dementors flying across the sky. So if you would like to call this the Dementor pillar. You can. But let's take a look at some of the other things, okay? So, oops, actually, I didn't mean to go that quickly. Let me go back to that image. Right at the bottom of this pillar, you can see this bright yellow region here, right down here. I'm going to zoom into that on my next slide. Okay. So, generally, the bright yellow has been these ionization edges. Edges of dark clouds that are lit up yellow. And you can see on the left-hand side of this image, you can see an ionization front along here, right? So it's dark gas on one side and ionized gas on the other. This one here, this big yellow spray in the center of this image, I'm not sure what this is. And I didn't get a chance to ask the PI about this. This is a bright yellow, what looks like an ionization front, but it's not on the edge of a dark cloud. Right? This is what looks like, to my untrained eye when I first look at it, go, oh, that's a jet. No, it's not a jet. It doesn't really have a star-forming star associated with it. And then you look at it and you say, well, that could be ionization along a magnetic field. We see this a lot in the galactic center. Bright lines of strong magnetic lines going across there. So I am not afraid to admit my ignorance about this. This is a really cool feature about this image that smacks of almost either magnetic fields or it looks a little bit like the tendrils that we sometimes see in supernova remnants, right?
Mm-hmm.
And I don't know. Did you ever get a discussion of anybody that told you what this is, Tony?
No, I haven't heard anybody be able to tell us what that is yet.
Yeah, so I mean, this is a really cool thing. And you know, I like to say that, you know, some of the best days for an astronomer are when they realize they don't know what they're talking about. When you recognize your ignorance, then there's something new to discover. And this would be something new for me to discover in terms of this cool stuff here.
And this is something we would not have gotten with the older camera anyway. So the new field of view was something made, you know, seeing this was made possible by the new field of view.
Exactly. This is outside the field of view of the old camera.
Right.
Also outside the field of view of the old camera is this delightful part of the image.
Yeah.
These are much smaller versions of the pillars writ large in the big image. Matter of fact, the one on the right, Zolt-Levet, the image processor, refers to that as mini-me, you know, in reference to, what were those movies?
The Mike Meyer, Austin Powers.
Austin Powers, yes, the Austin Powers movies, okay?
Yeah.
So the mini-me in that, well, here we have a Hubble mini-me in the Eagle Nebula with these pillars. And really, when you look around the nebula, you see a bunch of these small little agglomerations of dense gas that are being eaten away. Now, these I would expect are going to be eaten away before they would have any chance to form stars. You might look at them and say, okay, there's a dense knot of gas here. Perhaps it might form a star, but at this scale, it's not enough probably to resist the erosion before it forms a star. So one of the things you can learn about is that the process of star formation, after other stars have formed and are then create these winds and ionizing radiation that eats away the gas, it actually will inhibit other stars from forming. Okay, all right. So that's it for the visible light image, but there's more, because the Wide Field Camera 3 doesn't have just visible light, it also can do infrared. So here is the new visible light image, and using the infrared portion of it, we got this image in infrared.
Yeah, that's my favorite part. Yeah.
And just to have fun, I'm gonna blink back, go back to the visible light image, and then go forward to the infrared.
Right. So the first thing that stands out are all the stars that you can see, right?
Amazing number of stars.
Right.
Yes.
Right.
With the infrared, you have longer wavelengths. You will see through some of the gas that you cannot see through in optical light, and so you'll see through and you see all the stars in the field.
So all the dark stuff that you see now is the stuff that's even too thick for infrared radiation to get through.
Exactly. Right. So the longer wavelengths can pass through low-density gas, can't pass through the really high-density gas. So what's left is the really high-density gas. And also the fact that stars appear different in the infrared. Right? With the infrared, you're going to pick out the cooler stars, and there are more cool stars in the universe than there are hot stars in the universe. So you're also going to get an extra complement of stars simply because you're bringing up the cool stars that you otherwise wouldn't. Okay?
Yep.
So let's put the two of them side by side. And again, we were talking about the number of stars that you can see here. And you can get a feeling that the structure is similar, but that they're slightly different. And one of the things I like to think about, because, you know, we do three-dimensional visualizations, right?
Mm-hmm.
And so when we're looking at the visible surface of a nebula, whether it's this nebula or other nebula, because the infrared penetrates deeper, you're actually looking at a sort of a three-dimensional surface underneath the visible surface. So you can think of the infrared as seeing, you know, below. If the visible light is the skin deep, the infrared, you know, goes a little bit deeper, and we'll see that the organs and other things, the details under some of the details underneath the skin of the nebula, and you can see a lot of structure. So let's go and let's do the same thing we did with the visible light image, doing 1995 to 2015. But now we're going to do both of the 2015 images, visible versus infrared. So if we start with that pillar, the central region where we had that smokestack. You can see here on the left-hand side, there's the smokestack with visible light. And then over on the right-hand side, you can see the infrared version of it, and you can see an amazingly bright star at the top there.
Right.
Which I'm not sure that that's the star that is formed.
Oh, really?
Star that is formed at the top there.
Oh, okay.
I tried looking at it in great detail, and I couldn't convince myself that it absolutely had to be that a star that had formed at the top of the smokestack. But it sure looks like it, doesn't it?
Yeah, and if you look at the top of the other one, you can see a star there as well. Then there's light on the right, on the left image. It looks like there's something right behind that gas cloud that is shining pretty brightly, and it looks like it's coming through in the infrared image. But maybe you're right. Maybe it's just a.
It could just happen to be a coincidental placement, and so I wouldn't want to tell our viewers that it absolutely is, unless I knew for sure. But you can see it. But the other thing that you can see is that if you look in the left-hand image, you can see these two stars in the lower right. Okay.
Yep.
Those stars in the lower right. You find the corresponding stars in the right-hand image, and they're honking bright. Right?
Yeah.
You know, so a faint star in the visible light image might become a very bright star in the infrared image. Okay. Let's go to the top of the central pillar. Again, visible light on the left, infrared on the right. This is one of the times that, remember the Horsehead Nebula, Tony?
Mm-hmm. Oh, yeah.
When we went from the visible light image, you saw almost nothing with visible light in the Horsehead. And then when you went into the infrared, you saw an amazing amount of landscape that sort of appeared by looking into it. This is sort of the opposite. I actually feel like we lose a little bit of detail in going to the infrared here. We don't get as much. There's an awful lot of dense gas here, right?
Yeah, but it seems to me like, yes, that's what it tells me, is that just how thick and dense that material is, but also that the structure that you see on the left is actually pretty superficial. And it's not doing much in the way of infrared emissions at all, because it goes away. It's dark in the infrared. So.
Right.
Yeah.
So I mean, this is a seriously thick mountaintop.
Yeah.
This is this is a dense glob of gas that's really, there's a lot of stuff there. All right. You can see how that tiny star in the low in the center down bottom becomes a nice bright star in the infrared. The other thing that you see is you do see some star formation. I do see some star formation up here at the top of the pillar. You can see these two bright stars. Okay.
Mm-hmm.
These look to me like newborn stars. You can see the red region on the left, where you can see one of those stars looking like it is just formed in the top of the pillar, and then you see through a bit and see another one here in the infrared. So again, looking in and seeing details of the star formation that's probably going on inside these pillars, and the jellyfish is really faded out.
Mm-hmm. Yeah, you can barely see it in the infrared.
Okay. That star formation is shown also in detail at the top of the tall pillar. So if we go to the top of the left pillar, again we see how all of these tall little fingers, these small little fingers, are actually, in the infrared aren't quite as detailed, but they're also bathed in all of this evaporating gas. So all of this bluish, grayish light in the infrared image is that evaporating gas that sort of colors, that gives us some color in front of the gas. So sometimes I'm not sure we can see just how much detail, how much dense gas there is, because there's all of this evaporating gas on top of it. And you can really see the detail of star formation if you look in this region here. So I put these arrows at the same spot in each image, and you can see on the visible light image there's that little red glow. All right.
Oh, look at that! And yeah, you can still see it, but it's brighter in the infrared. Yeah.
And in the infrared, you can see that there's star formation going on in there. So that little red glow, a place where a star looked like it's forming, has become eaten away. You can start to see that there's a cavity in there, and that's where a star is forming. And this is what I mean about being able to look deeper inside to see what's going on. And when you've got these stars somewhat near the surface, that the cocoon around them is forming, you can actually, with the infrared, see them. Now, this, of course, is just what we call the near infrared. Hubble doesn't go very far into the infrared. We need something like Spitzer or the upcoming James Webb Space Telescope to see deeper into this, and then you can see all sorts of interesting and more detailed structures inside. Matter of fact, sometimes when I'm comparing Hubble and Spitzer images, it's really hard because you're looking so deep into it that the structures don't really match. Sometimes the structures don't match. So, all right, one more thing.
Okay.
Actually, two more things. Two more things about this. The real difference when I look at the visible light versus the infrared light is actually from a much larger perspective. So here we have that leftmost pillar on the top. And when you look at the visible light image over here, it feels like it's a solid pillar up and down, right? That, you know, but we know that it's only required that the top part be dense and that the part down here could be in shadow. Well, when you go to the infrared, what do we see? Well, actually, we see a whole lot of emptiness.
Yeah.
Okay? There is a really dense cloud up at the top, but all of it, you're seeing so many stars through here and not much gas that this is shadow. We are seeing emptiness in the infrared that we otherwise couldn't see using the visible light. And this is one of the most important things that infrared allows us to do. In looking through the low-density gas, we get to see, I hate to say it's like an X-ray, because that mixes a lot of light metaphors here.
Yeah.
But you get to look through the visible surface and see what's truly underneath. Where is the really dense gas underneath this? And you can see that that pillar isn't a pillar. And if you study the infrared image, you actually get to see that the pillar is composed of a segment of several clumps with their shadows behind them to create that big, long, 3 light year long pillar. Well, that's kind of cool. And the other thing is that if you look, you will find some bright stars in the infrared that do not show up in the visible. So I know you're looking at this going, well, what's he comparing here? Okay, this is the exact same region from both images. Okay.
Boy, you'd never know that. That looks completely different.
You look at this and you go, what's he trying? Okay,
Yeah.
So let me guide your eye here. Okay, on the left-hand image, you see these 4 stars here: Bing, Bang,
Yep.
Boingo, and Bongo. Right? Come over to the right-hand image, and you see the same 4 stars: Bing, Bang, Boingo, and Bongo. All right, those are technical terms.
Yeah, I wonder if that's the IAU.
You're not trying this at all.
I'm sure the IAU has them named that too.
Where did these 4 honking big infrared stars come from?
I know, they are really bright.
And I remember you and I were at the AAS, and we were looking at this on the touch screen, and we said, oh, those 4 stars have to be these 4 smaller stars. And because we were just sliding back and forth, we weren't able to crossfade back and forth. And so when I brought this into the image processing program, and I aligned them and everything, and I went down here, it was like, oh.
Yeah, those aren't. Uh-oh. Are you there?
Must be behind, wow, the green gas, the blue gas, the oxygen emitting part of the nebula. And that only with the infrared do you see through it in order to see these really, really, really bright stars.
Cool. All right.
So that takes us to our final slide of today's presentation. On the left is the 1995 image. The center is the 2015 visible light. And on the right is the 2015 infrared.
Oh.
We have revisited a legend. There is so much cool stuff to look in here. I got to say that the visible light image and all 60 million pixel glory is available for everybody, not just astrophysicists. The public can download it and look at all these cool details yourself. The infrared image is something like, what? I think that's around 16 million pixels. Yep. As well. So there's lots of all the data. One of the best things about Hubble is it's not just the astronomers on the mountaintops telescope. It is the people's telescope, and all of our data, all of our work is paid for by the public, so all of our data is made available to the public. Yep. So if you go to Hubble site and you want to study these images and details, have at it and enjoy yourself.
And nobody knows that better than the person whose question I want to get to right away. Judy Schmidt. She is. Hi,
Ah,
Judy.
Judy.
She's always a good person to talk to about Hubble images and using the data, things like that. But she's asking a question. She says, "I like to call that reddish protrusion from the center pillar a kabuki mask." I wonder though, and I'm going to put it up here. I wonder why its composition is a little different from the rest of the pillar. You got any response to that?
She calls it a kabuki mask. I actually looked at it as an ear when I see it there. The red color there, I don't have a good guess for it, to be honest with you. I know that, the red in that image has got to be nitrogen, and let me go back to that. Let me see if I can quickly go back to that image. I'm going to scan through real quick. There we go. Whoops.
Okay.
Okay. So on the left, that I believe this is what Judy's calling the kabuki mask. It's not so much the red dot on the left-hand side of it that seems reasonable. It's these sort of scallop shapes around it that I don't quite know how that would. I sort of look at those things and I start to think of winds, etc. From newborn stars to blow out, because this looks like billowing out of a wind. As you blow out bubbles and such. But that's going to be my best idea for something like that.
Okay. All right. Well, it's going to be a while, I guess, before we can find out everything there is to know about all these images. But that's a good question, Judy. Nicholas has a comment, or actually his questions are about the differences in resolutions. He's asking, is it really only, this is between the two cameras, is it really only the better resolution on the newer images, or also some more 2015-ish image processing? So to what extent do you think the details that we're seeing are due to the better image processing techniques versus the better cameras?
There's a little bit of that. Okay, so first of all, there's the cameras. With PIC2 is a 1/10 of an arcsecond per pixel. With C3 is a 20th second per pixel. So that's definitely there. Two, the detectors are more efficient, and well, they can do the same image in shorter time, but they our understanding of how to process the data is, of course, better, right? We processed the WIFPIC2 image. We had only 2 years of working with WIFPIC2. We've had 5 years of working with WIFC3. Computers are much, much, much faster. We know how to remove errors. There are some errors, by the way, that if you compare the two, you can go, oh, that's not a star. That's a glitch from the bright star creating a peak in the CCD. So there's some of those small things there. So it's improvement in resolution, improvement in the detectors, and improvement in our processing that do help all of our gaining more science from these images.
Right, and
one
point I'd like to make is that you can also with the when you have the data from the original camera, there's nothing to prevent you from reprocessing it using new techniques once you understand how to better do things. The only thing you can't really do is maybe take different calibration images or things like that because the camera is no longer there. But there's nothing to prevent you from using the newer techniques.
Right.
So okay, so I think I will. Let me look to see if there's any more questions around. I'm looking at Hubble Hangouts. I don't see any tweets or anything. So the only other question is from Zigzag, and I'm not quite sure how to interpret this. But do we have any idea of the rate of mass expansion? Oh, it just disappeared. Oh, great. Where'd it go? The idea of the rate of mass expansion in miles per hour, and we talked about that briefly. If you're talking about the increase in the rate of the or the movement of some of those features, we didn't know it off the top of our heads, but you can figure it out by knowing the pixel scale, which is the area on a side of each pixel, and then count the number of pixels. And since we know the time, there was 20 years have gone by, we can kind of get a speed from that as well. So that's the way in which you would figure it out.
The scale on this is going to be on order of 1,000 kilometers a second. Okay.
Yeah,
the solar wind. Okay, the sun's a middling star. The solar wind from the sun blows out at 400 kilometers a second radially and 800 kilometers a second vertically. The jets are going to be at faster speeds than that, so they'll be a few thousand kilometers per second, maybe as high as 10 or 20,000 kilometers a second. Now, a kilometer per second, if you do the math, ends up being, what do we get? 30 kilometers per second is about 100,000 kilometers per hour. So, you know, you're multiplying by large numbers, 3,600, in order to get these things up to per hour. So
right.
Very, very large numbers in terms of per hour, but a couple thousand kilometers per second, which is how astronomers think of it.
Right.
Okay.
Okay. Well, thank you, Frank. This has been awesome. I'm going to stop it there, but I want to remind everybody that we have a new Hubble public lecture next week, and we will be broadcasting it on YouTube. I also wanted to point out, I should have done this at the top of the Hangout, but I didn't do it. On Monday, the ESA, the European Space Agency, is launching a video contest called Ode to Hubble for Hubble's 25th, and I'm posting it right now on the event page. I just posted it. The link to where you can learn more about it. So if you have and they're taking all video submissions, I think under 3 minutes. So if you have something about Hubble you'd like to say, or a message you want to send Hubble, then you can enter the contest, and I think they're going to discuss what the prizes are going to be. I'm not quite sure what they are yet, but keep an eye out on that web page for it, and make a video. Make it under 3 minutes and submit it, and who knows what'll happen. And they're taking 2 categories. One of them will be for people under 25 years old. Those are the people who they're calling a Hubble generation. These are the people who don't know a world without the Hubble Space Telescope. And then there's entries for those over 25. So keep an eye out for that on Monday. We'll be tweeting about it and sending out more information once that launches. So there's that. Also, tomorrow we have our regularly scheduled Hubble Hangout, where we're going to be talking more on the history of Hubble with Carolyn Collins-Peterson. She's an author who has written many books on Hubble, as well as Antonella Nota. She's the ESA program head at the Institute. She's going to give us some ideas. She's going to give us a brief overview of some of ESA's role in the history of the Hubble Space Telescope mission. So we hope you guys will watch that then. Frank, this has been fun. Thank you again.
Thanks, Tony. I find it surprising we could have this much to talk about one image, but I will.
I'm not surprised at all.
We'll return to the multiple stories next month, and we'll definitely get to Andromeda, because that was something I really wanted to fit in today as well.
Yes. Okay. Good. So I wanted to ask you about that. So are we going to do a Hangout next week also?
Why don't we do it in 2 weeks? Okay.
In 2 weeks. All right. So in 2 weeks, look for another news from Hubble and across the universe with Dr. Frank Summers, and we will talk about all kinds of things. Hopefully we'll get to the Andromeda image as well, like he said, which is another really incredible feat. So I can't wait to talk about that with you also, Frank. All right. Well, that's it for this week, space fans. I do that every time. I want to thank you all for watching, and as always, keep looking up.
Okay, we have certain legendary images. When you think of Hubble, there are certain images that you say, wow, that's something that just is so cool, that will live forever in your memory of Hubble. I think perhaps the most famous image Hubble has ever released is this one, the pillars in the Eagle Nebula, poetically named the Pillars of Creation.
And when did that first come out?
This one was first released in November 1995.
Yeah,
okay?
That is definitely an iconic picture.
Yeah, and matter of fact, you know, November 1995 was an amazing month for us, because not only did we release this image, but we also released that beautiful image of the trapezium cluster in the Orion Nebula. That first Bob Odell image of the Orion Nebula getting into the trapezium, it was like 5,000 pixels across, by 5,000. It was amazing. So that all came out within 1 month. So that was a good month for us. But this one is one that people always remember, and it's nicknamed the Pillars of Creation simply because these are places where stars are forming. All right, so you have these long, tall pillars, and they're being blown back by gas from hot stars that are forming in this cluster. And in the very tops of these pillars, and I'll show you some of the details in a bit, are places where stars are actually forming. And so hence that's where the nickname Pillars of Creation comes from. But let's back up a little bit. Let's actually give you a little more context, and that's when you can see the teapot. Okay? And for those of you who think of astrology and think of that you're born under the sign of Sagittarius and that you're supposed to be a goat herder, no. Remember the song we had? You are a little teapot, okay?
Don't sing it, Frank.
I won't. You didn't like my singing last time.
Oh, it was fine. I'm just not going to join in, that's all.
Okay. Anyway, so there's your teapot. All right, so let's zoom into M16. Whoops, I hit the wrong button. There's the button. Okay. So this is a beautiful image. It's a ground-based image from a website called clearstarrynights.com. I couldn't find the name of the person who does these images. He didn't put a lot of these websites put their names and their credits all over the place, but this shows you perhaps why it's called the Eagle Nebula. I wanted a wider base view so you can see sort of the wing extending to the lower left and the head up at the top left, and the spread of the wings of the eagle sitting in front of you, right? You can sort of, can you see that, Tony?
Yeah. Do you have the ability to use your cursor at all to kind of circle what you're talking about, or?
I do, but it's that this screen is such high resolution.
Oh, yeah, I can see it though. Go ahead and circle.
Okay, all right.
Circle where you're talking.
There you go. Okay, so that's the head.
Yeah.
Okay, and then if you follow down here, you can see the wing.
Hello, everybody. Oops, I have to push. Hello, everybody, and welcome to this week's Hangout. It is time for our news from Hubble and across the universe with Dr. Frank Summers Hangout. We do this every month. Generally, we try to anyway, and it's usually coincides with our Hubble public lecture series, which is generally held on the first Tuesday of every month. Because of some scheduling issues, we're having it a little bit later in January, plus we had the AAS earlier this month. So we are having it in the last week of January, but that gives us a good opportunity to talk about next week's Hubble public lecture, which will be on Tuesday. It's generally rebroadcast on YouTube, so I'm usually on hand to respond to questions and comments while the lecture is going on, but we invite you to watch it after the fact as well.
So let me just give the plug promo for that.
Okay, go ahead.
Dr. Jason Tumlinson of the Space Telescope Science Institute. He will be speaking on one of the longest titles I've ever been given, From Cosmic Birth to Living Earth, the next great space telescope beyond JWST. So, I mean, we're already looking forward to the James Webb Space Telescope, which doesn't launch until 2018, but Jason's going to come and talk to us what happens after that.
Right, and we've also had a couple of hangouts on that as well. So yeah, so you're right. We are actually starting to look beyond the Webb.
For this, so we're going to explore this in great detail. So this is an image of the Milky Way center of the Milky Way galaxy from Akira Fujii. Akira is wonderful and lets us use a lot of his images here at Hubble. And what has been drawn out here is the locations of lots of different Messier objects near the galactic center. You can see M16, M18, M25, M23, M20, etc. But the one that's been boxed in there is M16, and that is the Eagle Nebula. Now, some of you may not know when you're looking towards the galactic center, you're not going to have this good seeing. Just to show some of you, the constellation Sagittarius is drawn in the lower right, and I'm going to put in the constellation lines for you. The constellation lines, yes, the teapot. This isn't the entire constellation of Sagittarius, but it's the only part of the constellation of Sagittarius that I know. Okay, so
yeah, it's the part everybody recognizes. That's what I all learned on as well, is how to find the teapot.
Exactly. You got to find the teapot, and then you're actually looking towards the center of the Milky Way. For those of us in the northern hemisphere, You're only going to be able to see this in the summertime, July and August, and it's going to be low on the horizon. All right, so the center of the galaxy is not going to be visible in winter. It's only visible in summertime, and it only gets, tens of degrees, 30 degrees or so, 40 degrees above the horizon in the summertime.
Hubble Space Telescope. So definitely check that out. I will have it on. It's at 8 p.m. Eastern Standard Time, and that's when it'll be broadcast on YouTube. And so we'll look to see you there. Before we get started with Frank today, though, let me just tell you we hope you'll bring us some questions and comments for today's hangout. We have. I'm looking at the Q&A app. That's the best way to interact with us. But I'm also looking at Hubble Hangout hashtag, as well as the event page on Google+, and the YouTube page this is being broadcast on. So please bring us your questions and comments, and we'll try to read them out while we're on the air. Hiya, Frank. Welcome back.
Hiya, Tony. How you doing? It's been a long time since we chatted, because we had AAS this month, which postponed this month. But
that's right.
Also last month, I was at the American Geophysical Union conference, and you had a vacation, so I don't think we did a December hangout.
No, we didn't do a December hangout, so we missed that one.
It's been since November, so welcome to all our friends who are joining us. There's a ton of stuff to catch up on. We're not going to get through it all today, okay, unfortunately, because I got so much cool stuff just from one image, really. Well, one press release. It's just really lots of fun.
Okay, so yeah, so go ahead. What do you got for us?
Okay, so I am going to talk to you today. This is our news from the Hubble and across the universe, and I will be my story for today. And I apologize there isn't more than one story today, but we got lots of cool stuff here about this. Okay, revisiting a legend.